Hello, and thank you very much. And okay, let's revisit, because there's some new people, so that's important with this sort of thing. And then just regroup where we're at. Okay. What we've been talking about is regenerating the landscape, right? So the whole issue of instead of just, but not that we're negating it, instead of just drawing down emissions, we've got actually a much more series of areas where we've actually got to, instead of just reducing emissions, we've got to also draw down significant emissions of carbon from the CO2 sort of situation. And so really a lot of this earlier section we were talking about, that drawdown and what all the science and background of that drawdown story is. And sort of, then we were saying, okay, that's the drawdown issue. There's another big part of the equation, which we want to talk about now. And that's really, instead of, or on top of drawing down, we've also got to cool the climate. Because, just to get into that, we basically emitted, it's 400 parts per million at the moment. Okay, it's locked in to go well above 500 parts per million by 2030 because of ocean lag effects. We went through all that. And so that's going to lock us, and I mean everybody's agreed now, that's going to lock us into 4 degrees warming globally, within a matter of decades.
By when, do you know when exactly?
Well, no, we're not exactly, because, I mean, we'll come into that, because there's a lot of, Alex, there's a lot of other questions, and we're going to be talking about cooling. We're not going to let it get there, we're going to not let it go much beyond 1.5 degrees centigrade, right? Because if we do, it's cactus.
Yeah. Because
basically, biosystems can't survive. And we haven't, you don't know any about this yet, but the point is that photosynthesis, right, effectively stops much above 38 degrees centigrade if the plants can't get enough water to keep themselves cool. Okay, so the whole basis of, oh, come on in, and seats at the front, and there's lots of, please come on in. And just, so look, there's a lot of feedbacks in nature. And in a sense, the planet has naturally kept itself cool. We can go all through that. And so photosynthesis stops. So we can't afford to let it go anywhere near 2 degrees, let alone 4 degrees. 4 degrees is literally meltdown, total collapse, right? So this afternoon, we just want to talk about that cooling thing. But before we do, I just want to reintroduce all the new people and stuff like that, and just sort of basically go through it. I'm a soil microbiologist. I used to work at CSRO. I've done, like soils and forestry and tropical crops and pastures. I also worked for about 20-odd years with government in Canberra, Barry Jones, John Button, commercialising innovation, national strategic big picture stuff, where we have to go. Last 10 years I've been retired. I've been formed a little NGO with other farmer colleagues, and it works, Healthy Soils Australia, and we're all about soils regenerating landscape. Last 5 years, I've been working very much with Michael Jeffrey, the ex-Governor General, who also, after retiring, passionately took to this, I think. Look, it's that landscape, it's everything, water, soil, future. And and so that's what it's about. And so really, this is, in a sense, what we're doing. Healthy Soils, we work very much underground, like we're not really noisy out there. It's always working with farmers. We work with about 1,000 farmers all over Australia, but very strategically in different areas. And it's all about, how do we document, provide evidence, facilitate innovation, leading innovation with those farmers, and then how do we multiply, extend that to 12,000 farmers. 12,000 farmers, 10% of the farming base, that's our tipping point, right? Because if we can get those 12,000 implementing it, they're all aware, we're all, done all the awareness, but if we can get that implemented, that's the tipping point, right? So look, that's where I am, and we want to talk about all those things, but if we can pretty quickly go through and, just introduce yourself, but also just ask what it is that you want out of this workshop, if we can, but fairly quickly if we can, So Annie.
I'm Annie Nielsen. I'm from Parramatta Climate Action Network. I was a science teacher, but I don't know a lot about soils. I taught a bit about soils at school with the kids, but not very much. And I really am interested to understand exactly how it works, because I don't understand how it can work.
Are we doing it?
Oh, well, if you want to pass, yeah, okay.
My name's Anthony Lewis. I'm also from the Parramatta Climate Action Network, and I'm an engineer there. So we obviously buy a lot of food, and we want to know the soil.
Okay,
You know, so.
cool.
I'm Keith from the Carbon Reduction Institute. We certify businesses and products as carbon neutral. And I'm currently doing some work with vineyards, and they're real keen to try and get some benefit for the carbon in their soil. So I'd love to be able to offer carbon offsets for soil carbon.
I'll see before.
Before.
I'm Harry Greenwood from Port Macquarie Climate Action Group there, and it seems to me that the farming group is one group that we could reach, really. When the politics fails, it's like renewable energy, it's what you do, you know, it's something that can be done.
And if we don't reach them, we're cactus, right?
Yeah.
Farmers, no water, no food.
Yes.
John Davis, I'm in the Climate Action Working Group for the Greens, and we've got to try and work out more details about Tony Abbott's soil carbon.
Soil carbon story, okay, yeah, coming to that.
Tony Muscio, in the relation to soil, I'll announce myself differently. I own 100 acres and I have 650 acres of ground land next to me that I want to take custodianship of, and on my own land I want to do bush regeneration, and I have a number of areas that need regeneration, and I want to leverage soil carbon increases in that.
Okay, so all right, we'll talk about some of that, but we'll go back. Yeah.
Gavin McGregor, I support the Greens, and I'm a human being living on the planet.
Let's keep Gavin living on this planet, right? So what we had last time, obviously we had this sort of CO2 time, and we more or less sort of drew this graph, right, where basically, you know, this is Keeling, there's CO2 going up, and yeah, there's our 4 degrees C. And the point is, what we made the point is that, yeah, every year, Northern Hemisphere winter, we're emitting carbon, and every summer, green growth is actually pulling it back down, drawing down. But in a sense, there's a deficit of about 10 billion tonnes of carbon per annum, you know, in terms of that we're not, and because of that deficit year by year, this is of course going up, so there we are at 400 parts per million. And that's going to keep on going because we're talking about ocean lag effects, so it's locked in effectively. And obviously we've got to sort of get back down here to 350 parts per million, save climate, okay? And so the answer is we've got to not just do that $10 billion, 10 billion tonnes of carbon per annum, we've got to do this 10 billion tonnes of carbon per annum drawdown of old heritage carbon. So here we are, we've got a 20 billion tonnes of carbon per annum drawdown target. That's pretty monstrous because we're talking about 5% emission reductions. That's sort of like only 8 million tonnes, right? So this
Is carbon or carbon dioxide?
Carbon, always, yeah, okay, it's carbon, okay, the important point, we're talking carbon, it's about 3.7 tonne, a tonne of carbon is 3.7 tonnes of carbon dioxide, right? So we're talking carbon. Yeah.
It's billion, is it?
Billion, yeah, billion.
20 billion, yeah.
Billion, 20 billion, 20 gigatons of, yeah. So these are big numbers, but the point is that's what the deficit is, right? Of about 8 of this is from fossil fuels, and about 2 is from land management, right? And that's what the IPCC and all that sort of stuff is about. But we're way above them because this is really, no one's talking about this drawdown, right? But yeah, we have to do that. The point is, in the last session we talked about in detail, we can do it. Very fortunate because nature has been doing this over 420 million years. And it's a simple matter to say, look, we've got farmers doing 10 tonnes of carbon per hectare per annum. Okay, and we simply say, look, here's 100 million hectares of Oz, which is 15% of Oz rural land, and there you are, there's 1 billion tonnes of carbon per annum. So we're really saying, yes, we can. Comes back to your 100 hectares, Anthony. Yes, we can, but the issue is, yeah, what are the processes and tools and strategies and practical management issues to do that? And then how do we extend it? And of course, this is where my 12,000 farmers are. Some of my guys have got 1 million hectares. So to go in, it very quickly gets, yeah, we can do the 100 million hectares, 15% of the Australian landscape. So what we're saying is all doable, but it's not going to happen by accident, right? So this was the whole carbon story we pretty much focused on, and we had a lot of discussion about the science and all that, and there's a lot more detail. But I want to go beyond that, because this will take, you know, we do this year by year, but it might take a century, because there's 38,000 billion tons of carbon in the oceans. Okay? And what happens is that every ton of carbon we draw down, even we're drawing down 20 billion tons a year, hey, we've got 38,000 billion tons, which will re-equilibrate back with the atmosphere, because it's a beautifully buffered system. So we're not going to be able to stop this going, you know, to 4 degrees, even by carbon drawdown. Okay? It'll take 100 years, and it'll be too late. We'll be way over the threshold, tipping point, it'll collapse. We're locked into collapse. So we've got to do something else. We've got to, in a sense, cool this sucker.
Not the t-shirt slogan. Let's cool this sucker.
Yeah, we've got to cool this sucker. No, seriously, big time. Okay, so we've got to cool it, okay? And because you, me, we all want to live, right? And it is that serious. So we've got to cool it. So all that can go, because we're into the game of cooling now, right? And this is, in a sense, the sort of step 2. Now, nobody's ever talked about cooling to you before, because it's all been about, can we do a 5% emission reduction? Yeah, please, welcome. Can we do a 5% emission reduction? Oh, actually, we're doing a reduction. Hey, can we have an aspiration of a future 5% emission reduction? And I'm a politician and I'm proposing it to you, right? Or can I put a carbon tax in, and then we'll just see what happens, right? Something good happen.
That's a good shrug. Yeah.
I come from Canberra. Okay, so the point is we're talking about cooling. How do we actually cool this sucker? And of course we've got to change paradigms. Einstein sort of said you're never going to solve any problem with the same thinking that created it. So we've got to step out and see. And let's go right back to 4 billion years ago, when I was young. Okay, 4.6 billion years ago, what happened? We had a supernova roughly where Neera is sitting, and a big explosion, and a star, you know, bright and shiny. And okay, we had a supernova, and basically that created a cloud of hydrogen gas, which re-condensed and coalesced back into our sun in a hydrogen helium balloon, and a whole lot of stardust, right? And that stardust coalesced into these 9 planets. There's 2, they were arguing about Pluto, but anyway. So we've got planets, stardust, you know, 96 natural elements. And basically this is an inert world, and then basically whether we captured from a comet or what, we then had water. So from 4 billion years ago we had water on this planet, right? And basically it's that water for that 4 billion years that has actually governed the whole climatology of the blue planet. Okay? And again, I can put up all the slides, and I'm happy to cover them. This is a model of the hydrology of the planet from the Royal Swedish Academy of Science. But let's just do it very, very simply, because this is the guts that you never see. And that's our climate, that's our Earth. We're round, but we're not square, but we can do that. And so basically we have 342 watts per square metre of energy coming in, and this is solar energy, right? Coming into the Earth's surface. We've got 240 watts per square metre going out. So there we are. We're basically warming 2 watts per square metre every year, because we've disturbed this balance of energy in, energy out, and there's our global warming, you know, factor. Okay, it's actually about 3 watts, 3.2 watts, but we've got a masking effect because it's sort of dimming and aerosol dimming. But it doesn't matter. We've got to really, our bottom line is we've got to really cool this planet. That 3 watts per square metre.
That's what we've created.
That's coming into the top of the troposphere. That's going out of the top of the troposphere. And we have stuffed it up. We are retaining an extra 3 watts, so we're only losing 340 instead of 342, right? So we're retaining extra heat, and that's in a sense of nature. So we've got to cool this thing 3.3 watts per square metre on average, but it varies in different parts of the Earth. But, okay, and so we look at what's actually driving this whole heat dynamics. The first thing is we have clouds. And clouds reflect back out to space, and this is powerful, 0 to 60% of that solar radiation, naturally. On average, it's about 33% of that incident solar energy is reflected out to clouds. And this varies from place to place. You know, some parts very cloudy and very bloody cold, Scotland or somewhere, right? Because you've got clouds, and you know, I mean, clouds come over today, hey, it's cold, we've got jumpers on. Clouds go away, we've got sunshine, and we're down in t-shirts, right? So it's very simple there. There's clouds. Okay, and so that's the first thing. So the level of clouds governs how much is heat in the thing, in this whole planet. The solar energy that doesn't get absorbed with clouds, so then comes down and actually it hits the land surface. Now, if that land surface is green, we've got an albedo effect on the land surface, and again, that can be sort of basically 8% of that incident solar radiation going back up, so it's in the order of, you know, we'll just say, well, varies again, it varies enormously, but basically just say it's 30 watts per square metre, squared, and that basically again is what this vegetation, you know, albedo can influence. About 2% is actually taken up as energy to actually do photosynthesis, right? So there's about 7 watts per square metres, which is in a sense what we use. And this is actually quite stunning because this is physically quite interesting. Okay, so that's the albedo effect. But what this vegetation does, and we talked about the extension of green growth across Australia, what this vegetation does, and here's the litter and the grass and stuff, it actually protects the surface, right? It protects the surface. And so the difference is if you have vegetation, you might have the soil temperature not going above 20 degrees centigrade, because it's always even in tropical areas, okay? Mostly it's 15 degrees to 20 degrees centigrade. You know that if we clear that vegetation and that same solar radiation coming down there, and just say you take a bare soil or an asphalt or a car park, now it can go to 50 to 60 degrees centigrade, right?
Yeah.
Hot, hot. And that's your urban heat island effect, that's your bare soil. We had data up before, remember we created 5 billion hectares of bare exposed soils, right? So there's this vast difference in temperature. Now here's something that's sort of inescapable, it's hard physics, it's a bit like gravity. It's called the Stefan-Boltzmann equation, black body radiators. And basically the re-radiation of energy that hits that land surface has to escape, so you know what goes in goes out. It comes in as short wave solar radiation, and it goes back out as long wave infrared, okay, heat. Okay, but there's an equation that governs that you can't escape. It's like gravity. The re-radiation is proportional, a constant, to the 4th power of the temperature difference.
Yep, that's obvious.
Okay, what it means, if we've got a 40 degrees difference in temperature, it's 40 times 40 times 40 times 40 re-radiation, right? So to go in, it's a powerful factor. So what we do to our land system massively changes how much heat is absorbed and how much comes back up as re-radiation. It is this long wave re-radiation that is the principal factor in the natural greenhouse effect, whether it's water vapor or whether it's CO2, right? So we've always sort of, okay, now we'll draw a little balloon here and we'll take that space over here to draw that little balloon. We've tried on this before. Okay, so basically what I'm saying, a key variable in the natural greenhouse effect isn't the number of CO2 molecules in the air line, it is actually how much is re-radiating from that land surface. We've got a lot of CO2 molecules in that space. We've got 400 parts per million of CO2 molecules. We've got, actually, let's call that, yeah, okay, well, we won't draw as many. We've got 40,000 parts per million of water vapor molecules. today, we've got 40,000 parts per million water molecules up there, 4% moisture in the air. Okay, that's 4% moisture, that's 400 parts per million. And so basically there's a ratio of 100 to 1 in the number of molecules out there. Each molecule of water vapor, there's water, there's carbon dioxide, CO2.
Can I just ask a question?
Yeah.
That 100 to 1 is the actual water vapour compared to the rest of the atmosphere. Is that right?
We're talking now about the ratio of molecules
Oh.
causing
400
the
to
natural
40,000.
greenhouse effect.
Yeah, there's
No.
water,
Water-
CO2,
water
vapor.
CO2 and
100
water.
water,
Yeah.
1 CO2.
So what we're saying that there's by weight, there's 40,000 parts per million water, and by weight there's 400 parts per million of CO2. So there's 100 times difference. So we've tried to do this 100 to 1.
It's by mass of our molecules.
Now hang on, again, good question, John. This is just, now we're talking about by mass. But we know this has got a molecular weight of 18, and we know this has got a molecular weight of 44. Okay, that's
Now-
the
now
weight
we
of
do.
each molecule.
There we go.
And basically, therefore, there's 2.5 times. So not just is there 100 more, I mean, not just there's 100 more by weight, but each molecule is, 40% of the weight, so times 250 water for your molecule. And each of these water molecules, because this is actually the hydrogen oxygen bonds that can absorb a lot more heat than these carbon oxygen double bonds, they're more rigid, locked in, it has about an 8 times heat absorption effect compared to the CO2. Okay, water, it takes, so the latent heat of water is say 596 calories per gram, carbon dioxide latent heat of about 72 calories per gram, right? So it's got about 8 times the water absorption capacity. So you're going to say 250 times 8, and so that's a relative difference in the heat absorption capacity of water vapor molecules, 250 times, and compared to the carbon dioxide. So you can very quickly see why water vapor is the dominant greenhouse variable, right? So that's all I'm trying to do here. Water vapor, and that represents 80% plus of the natural greenhouse effect, and there's CO2, which is about 20% of the natural greenhouse effect, right? But in fact, the biggest variable is this level of re-radiation coming up. And I mean, this is a bit radical and it's a bit sort of disconcerting, because all our interest in global warming to date has been worrying about this 400 parts per million of CO2. And we've completely ignored the effect of land management on how much re-radiation is coming from this land. We've completely ignored the hydrology of this system to say here are factors that are 250 times, 8 times more effective water vapor vis-a-vis CO2. Now, the question, why have we ignored that? I mean, that's terrible. John?
The hotter land's going to re-radiate more.
Precisely. Yep, that's
So
what I'm saying.
So
Yeah.
you want more radiation. The forest is actually absorbing.
Okay, no, okay, yeah, okay, well, yes,
That
you're...
temperature's got to be...
No, but okay, this infrared, yes, we're getting more of that, but it's been trapped by these gases. You see?
Whereas the other one's been trapped by the Earth. What's the difference?
No, it's not actually getting to the Earth, because it's basically being re-radiated.
As short
The balance you're
waves.
looking for creates the trees that builds
Yeah, well, part of it builds the trees, but a lot of it is getting reflected, like on snow, right? A lot of it's getting reflected back out to space.
It stays
It's
short.
an
It
albedo.
stays as short
It
wave,
stays at short wave.
therefore goes through the greenhouse gases.
You see? So
Only
all I'm
when it
really
can-
saying that the things that are driving the natural greenhouse effect, there are variables here in terms of the soil surface and this water vapor that we've never considered. And taking Einstein's point, hang on, if we're going to cool this planet, it's about time we started looking at these elephants and being friendly with them.
So does
Bring them in the room.
shortwave radiation makes it through the...
Yeah,
water
shortwave
vapor?
radiation can get back
Oh,
out.
okay.
Long wave radiation gets trapped with the gas. Yeah, shortwave radiation just goes through all these gases like a piece of cake, you know, it's no
Other
issue.
side of the atmosphere goes
Yeah, it just goes back out.
But why is it short wave?
Yeah.
I'm sorry.
Okay.
Okay, I've just said, if you painted every bit of concrete and every road white and every roof white,
Yeah.
it would reflect back as shortwave.
Sure, if we put it all under snow, and when snowball
Oh, white paint?
it kept it very
I'm
cool.
just looking at my next investment, you know.
Yeah, no,
The
no.
white paint manufacturer.
Okay, no, good, yeah, actually,
We're running out of time.
T-shirts on the side.
thinking outside the square, investing in it. But no, look, I mean, yeah, snowball Earth, that's exactly what happens, you see, because once it goes white, once it goes ice, it all reflects, and it locks in cold, cold, cold.
It was serious, because people say we should paint our roofs white.
Yeah.
Would white paint do the same job as snow?
Oh, yeah,
It would, okay.
yeah, but the point is that, you know, like, then you've got to say, what's the embodied cost of all that plastic paint that you're going to have? Where's all the titanium oxide going to come from, and what's the...
They say you can put solar cells in paint, I don't know if that's going to work.
Yeah, okay, but what I'm saying, no, but we can grow grass, you know, white reflective grass, we can sort of manage, I mean, like, okay, but good stuff. We're thinking about smart ways, but we can do this because now I'm going to grow white clouds. Just, let's have a discussion. Okay, so the guts is, what I'm trying to really break up, we've just locked ourselves into this very, very, very limited concept of what's causing the dilemma. We've made the agreement that we're cactus, you know, we're locked into this disaster. We've got to cool the thing, and what we're saying, like the Swedish Academy, this is 1975, you know, so it's all confirmed, peer-reviewed, climatology 101, we've ignored it. But we've got these hydrological dynamics that are at our fingertips to use, and we can manage them all through this stuff, right? This vegetation. So how we manage the land is fundamental. Yeah, one of the questions was, oh no, John, you see, okay, so there's another dimension here. As we evaporate water, either from transpiration or evaporation from the surface, as this comes up, there's latent heat fluxes, right? And these latent heat fluxes is when water gets taken from a liquid back into a gas, and as we've said before, that takes 596 calories per gram. So water really needs a lot of water to go from liquid to, and that energy is then taken from the surface back up into the atmosphere. And that's in a sense cooling it. So the more water we can basically evaporate and transpire through this vegetation, the more cooling we get. And we know that because we know in a forest, like if we go to Kuala Lumpur, there's 25 degrees C in the forest, there's 43 degrees C outside in the bare fields 200 metres away. Same climate, same day. You know, this is the difference between these latent heat fluxes. We know that.
We're not getting it out of the atmosphere though, it's in the atmosphere still.
Oh yeah, no, okay, we're coming to that, right? Okay. So all we're saying is we've got all these hydrological dynamics, and really we're saying is, okay, if we're going to cool this climate, hey, we've got another whole dimension that we can sort of play with, right? What happens though is that, this is not that it's complicated, but okay, so all this water vapor is in the atmosphere, it's in these haze micro droplets, and of course they're just hazes. But to make dense, high albedo clouds, they need to coalesce, and about 1 million of these haze water droplets need to condense to make a dense cloud, which is in this high albedo reflectance, right? So all this water vapor we can get out of being a greenhouse active haze, and we can condense it into these clouds, and of course this comes down then as raindrops. Okay, so basically nature works, yeah, it evaporates a lot of water, it creates this water vapor greenhouse effect, but it also condenses it into clouds and then back into raindrops, and that's the hydrological cycle. And all we're saying, all of this is constantly cooling the planet, right? And that's how nature sort of cools the planet. And so we, through our land management, can actually rebuild, because if we're building this vegetation continuum, if we're building our, remember we talked about it, our in-soil reservoirs, the soil carbon in our soils, 1 gram of carbon can hold up to 8 grams of extra water in a well-structured soil, right? So because you're creating the sponge in that soil, and that sponge in the soil, that extra gram of carbon in that spongy soil can create the soil structure that retains up to 8 grams of extra water in that soil matrix. And that water is then available for latent heat fluxes going back up. It's there for maintaining the productivity and longevity of this green growth. So all the time, what I'm trying to really get at is that carbon, the drawdown of carbon, we're doing it not because we need to draw down carbon by itself, and that'll take too long, but every gram of carbon we put back into the soil re-drives this hydrological cycle. Okay, so rebuilding this hydrological cycle is actually critical to cooling the planet, and the carbon is the actual ingredient we need to sort of basically use to do it. Because that's, remember we had that little diagram of the oceans, and there's our rock, and this rock was just dry, desiccated, and it was basically carbon being put into this, which was then the start of soils, pedogenesis, and that was the start of the whole evolution of vegetation on land. And the same thing here, we've got to put the carbon back into the soil because it's the carbon that drives the hydrology, because there's its water holding capacity. Okay, the sponge. And it's very simple. I mean, it's a case of, yeah, you look at a tabletop, and if I put 10 centimetres of sponge on this tabletop, or I put a millimetre of sponge on this tablecloth, and then I pour a litre of water on the table, and you're going to tell me which one's going to have a wet floor and which one isn't. It's simple. And that's exactly what soils are, just a sponge. And we've got to rebuild that sponge, because that sponge is resilience, that sponge is the water holding capacity, that sponge is the longevity of green growth. We're in the driest inhabited continent on this planet. Our natural ecosystems evolved that sponge. Remember we talked about Oxley and Mitchell and Strzelecki and stuff like that. That's what our soils were. Interesting, if you look at Australian rivers, tell me one Australian river that has a delta on it when it hits the coast. No, Lake Alexandrina is, it's got, Lake Alexandrina's got 20 centimetres of silt above limestone. There's no bloody sediment, there's no sediment there at all. You see, none of that soil is eroded off because the natural landscape had a sponge and the water was retained in the landscape because of that sponge. If not, we would have had deltas, Mississippi, Nile, etc., etc. Yeah, some of the northern rivers are a lot of things. Yeah, okay, but yeah, I agree, because there's massive water, there's massive erosion. But even there, like most of the water is in a sense staying in the landscape in these in-soil reservoirs, right? And that's the unique, actually, that's the unique thing about the Australian landscape. I think a lot of deltas actually have been created by humans over the last 10,000 years, because we've eroded and degraded, and then of course, as we saw in Bundaberg, this last storm, there we kept creating a delta. I mean, we're creating a lot of sediment. Look at the chocolate going past that Bundaberg Bridge, right? But naturally, 15 minutes. Okay.
So if we've only got 15 minutes, can you tell us what we can do? And
okay.
Can you also tell us what might happen if by off chance the opposition gets in the power bottle?
Yeah, okay, all right. Well, good, Alex. Okay, yeah, all right. So, all right, what I was then trying to make the point, earlier we talked about carbon drawdown. I'm now saying, okay, we've got this other imperative, cooling, and the answer is, yeah, these things can reflect back 33% of the incident solar radiation. That's about 120 watts per square metre, right? A third of that. So it's very simple. If we have to get 3 watts per square metre extra, we sort of say, yeah, a 2% increase in permanent cloud albedos, because we're restoring that, can give us a cooling that existed naturally. It's that simple. Okay, this is latent heat fluxes. They take 24% of the incident solar heat back up here into these clouds. Okay, 24% of 342, that's what, 80 odd watts per square metres. Again, we increase that solar heat flux, we can actually cool. And so what percentage do we have to increase this, latent heat flux to get 3 watts per square metre cooling? Okay, so we've got this combination of natural hydrological regeneration options. And so the point is, we're putting carbon into soils, not just to draw carbon out of the atmosphere. It's not just a dead thing. That rebuilds the hydrology, that rebuilds the cooling. And it's a synergy, and that's how nature has cooled this planet, because basically, we didn't have ice ages before, we have ice ages now. And why? Because nature was able to cool this planet to avoid, in a sense, the Jurassic, Triassic heating sort of systems.
So what are you saying, that if carbon is added to the soil, that will automatically restore the balance?
Yes. See, that's the whole point. That nature, it doesn't think of things, but basically it is all synergistic. It is all. You can't have one without the other. Because once you've got the sponge, you've got water. Once you've got water, you've got cooling.
Okay, so how do we get the carbon in the
Okay,
soil?
we got the carbon in the soil. Remember we talked about it? Here's free CO2, sunshine, water. Here's a plant, and it was A, B, and C. Remember? A, B, and C. Here's photosynthesis. There's oxidation going back up to CO2, and here's polymerization through the microbial ecology, right? So we've basically got to change our land management. John, we were talking about that. We've got to change the land management to be this humate glomeland drawdown.
So what will that look like, though?
Okay,
In concrete
and when we
terms?
talked about that then in terms of these are then these grazing systems, these shelterwood systems we talked about. Okay, this is changing land management. There's not, I'm very nervous about saying here's a simple prescription, read page 55 of the textbook and everyone does it.
Yeah.
It is really like a doctor. You've got to look at the country, say, okay, what's limiting
So
growth?
some examples then?
Oh yeah, well here are case studies, 300 pages of case studies which is saying where leading Australian farmers have done that, right? Okay,
We'll put
Alex.
that up on the board in case.
Alex sort of said, okay, well what are we going to do and how do we do this, right? And of course,
with all the bush care sites around Australia in the cities, are they doing this sort of thing? And with that,
no, the bush care, no, see that's the trouble, this is new in the sense, no, they're not doing it because a lot of it is, and we talked about this earlier, tragically they're still interested in preservation. They're saying, okay, can I lock up this space rather than how do I regenerate this space, right? But, okay, so now the question of action. And from my point, it's very simple. Like, we're working